So today is just it's going to be a fun lecture just to generate your interest in fluids if you weren't interested yet. Maybe this is going to be the lecture that does it. So the plan for today is both of our TAs for the class are going to give presentations on interesting fluid stuff, their own careers. So they're going to give a presentation and then there's going to be time for questions with each of their presentations. I'm also going to talk about kind of some fluid stuff we didn't cover. So as you know, a lot of this course is highly idealized. So real world fluids, I'll talk about what's different there. And I'll also talk about some upcoming fluids courses and opportunities you have to do more fluids with this department. So I'm going to start by giving it to Michaela. Yeah, believe it or not, in 35 lectures, we actually didn't get to a lot of stuff. As I'm sure you just saw, there's a lot of concepts for real world fluid flows and even research grade fluid flows that we didn't get to cover in the class. So I'm just going to remind ourselves again of basically everything we didn't cover. So in terms of physics of fluids, I guess the biggest one is probably flows with non-constant density. So compressible flows, those occur in a lot of different industries like natural gas transmission, pneumatics, like compressed air. Flows with non-constant density also occur in buoyancy-driven flows. So in the atmosphere, um, the basically a lot of flow patterns in the atmosphere are created because you have a density gradient in the fluid. So it's not this kind of nice constant density incompressible fluid anymore. Um, so I guess if you ever have a chance to study those type of flows, you'll be very happy that we didn't do that in this class. Free surface flows, like watercraft design, rivers, lakes, and oceans, that's something that occurs in civil engineering, which is what Michaela worked on. So free surface means, you remember when we did hydrostatics and we have kind of a free surface, that's our zero gauge pressure. What happens when you have a kind of not hydrostatic version of that, so flow. So flow with an interface between water and air is most common. That's what a free surface flow is. Heat transfer, of course, as mechanical engineers, we want to extract energy from things. Certain things we want to cool down, certain things we want to heat up. So flows with heat transfer are a big part that we didn't cover in the class, as well as multi-phase and multi-physics flows. So that's a lot of what Mikhail and Pranav work on. So things with chemical reactions in it, like combustion or other chemical reactions, flows with phase changes. So if you have something that evaporates, um, for example, people study like boiling dynamics from a fluids point of view, and yeah, mixing as well of fluids. So immiscible fluids, and it gets the fluids gets as complicated as you'd like it to become, as well as turbulence, which is one bullet point here, but it's massive. It's probably the biggest field of research on this slide. So turbulence is something that occurs in all of these different types of flows, and it's still an active field of research. But luckily, we have, I would say, a couple hundred years worth of engineering experience working with real turbulent flows that we can draw on. So in this class, you learned how to analyze turbulent flows in pipes, and that analysis technique is what people are using in industry. So it's something that's doable. From analysis techniques, things we didn't really cover. We didn't talk a lot about CFD. I gave references to it at some point. But CFD is all about solving the Navier-Stokes equations using the computer. So right now I'll talk about like the modeling topics that are always hot in CFD is turbulence because it's very expensive to resolve. So I'm not sure who, I think maybe you asked about RANs versus DNS, that sort of thing. These are all different ways we can model turbulence in the flow, and it's mostly guided by cost. So resolving turbulence is hideously expensive. So you think computers are getting faster, GPUs are getting faster, um, but probably within our lifetimes, we still won't be doing DNS of anything engineering grade. It's the cost is huge, and if you take later courses in CFD and turbulence, you'll see that. Um, the other thing that a lot of people are working on right now is multiphysics. So how do we couple things like heat transfer fluids or solids fluid structure interaction? So yeah, it's all very complicated, but these are mostly driven by real world engineering applications. I would say a lot of fluids. There's not a lot of fundamental fluids research, researching fluids for the sake of fluids. That is interesting, but a lot of this is driven by real world problems that we want to understand and optimize in order to make things like reduce drag, more energy efficient, that sort of thing. Industry topics right now in CFD that you might be interested about. There's CFD is, you might think if you don't know a lot about CFD, it's probably along the same lines as where normal software has gone, where everything's kind of open source, everything's GPU now. CFD is a little bit behind. So there's a lot of opportunities and startups. People come up with new CFD techniques that work really well on GPUs, and they get bought out by these big CFD companies. So CFD software is an entire industry. So if you like software, if you like fluids, that's a very interesting industry to work on. So open source versus closed source. If you use CFD codes in your engineering practice, there's a high likelihood you'll be using a closed source software. So that's like ANSYS, Star CCM. These are pretty expensive software and they're closed source. But most software nowadays is open source. So there's this sort of rising competitive part of open source CFD software that can compete with these closed source software. So that's a big like tension point in the CFD market right now. Local versus cloud computing. So cloud computing is things like Microsoft Azure, AWS, these kind of cloud services you've heard about. There's a whole HPC side. So because CFD is so expensive, companies want to offload the cost of having to run their own server or buy their own machines and sort of on-demand access. So now you have to figure out how to run your CFD simulation elsewhere. Migration to GPU. So GPUs, we're kind of in the GPU era when it comes to machine learning. All that stuff is done on GPUs, but CFD is again behind. So it's slowly migrating to GPU. It's a lot of it is there, but there's a lot of basically money being made and opportunities in order to come up with algorithms that run better on GPUs. So that's a whole area you can work in. And also, of course, everything's got machine learning in it nowadays, especially CFD, because we have all these models, all these numerical algorithms, and it's very expensive. So CFD resolving physics is very expensive. So if you can use machine learning to save some money, there's a big driver there. Experimental methods is another thing we didn't talk a lot about in detail. So because this was kind of an intro course, we talked about a lot of theory. We talked about rough ideas behind experimental design and similarity, but we didn't talk a lot about measurement methods. So this isn't my field of research, so I'm just going to outline some important ones or ones that I think are interesting. So PIV and LDV. Um, PIV is it's called particle image velocimetry. I think I mentioned this before. Basically, you seed your fluid with a bunch of particles and shine like laser beams through it, and you can track those particles and use that to measure the velocity field. So that's a state-of-the-art technology, especially because there are some labs in the world that can do laser sheets from different angles and actually do like a stereo version of this. So normally PIV is limited to 2D, but you can get like 3D versions of this. So there's only, I think, one or two labs, I think, in the world that can do stereo PIV. Again, in the software that's being used for this, there's lots of closed source, old software being used, and lots of opportunities for machine learning. So I know you guys are mechanical engineering students and not software, but if you're interested in software and that sort of thing, there's lots of opportunities in fluids. So actually, maybe before I go on, are there any questions about that big information dump I just gave? Yep. Am I fine? Yep. I don't know. Industry leading versus lagging academia is hard to say because they're driven by different things. So I would say in terms of trying to squeeze efficiency out of CFD simulations, industry is almost always leading because academia isn't really about efficiency. It's about how do we come up with better models. In terms of modeling techniques, machine learning, that sort of thing, academia is leading. But the reason academia is leading is because it's kind of like the Wild West out there right now for machine learning and modeling and turbulence. So I think industry is a little bit like what's actually going to end up working. There's just a lot of research being done. It's a very active field of research. So I wouldn't say it's globally bullet points for bullet points. I would say whenever it's cost motivated, industry will lead, and whenever it's more accuracy motivated, academia will lead, and then industry kind of waits to see what techniques will be cost efficient or where the actual accuracy gains will happen. Any other questions about this? Yeah. Well, I mean, that motivates a lot of modeling. So, for example, if you want to do CFD to determine if your nuclear plant has a disaster, where's all the bad stuff going to go? Obviously, you don't want to test that in real life. So that's like why you motivate the modeling. So you have a rough idea of what it will look like because of the modeling, but modeling comes with its own issues, right? That's really tough. That's like a very hard problem. So if you have absolutely no data on it, it's basically you can't. How can you validate your model? So usually it's kind of a building block. So usually you validate because if you have data, then why do you need CFD? So usually you validate on a close case, and then it's your judgment to say, okay, I think that that's close enough to that this can be extended. If that makes sense. Any other questions? Yeah. Yeah. Yeah, I would if there's an area that you're really interested in, I would see if you can find out which professors here are doing research in that area and just start talking to them and tell them that you're interested. And it's never too, I wouldn't say it's ever too early to start here. There's just going to be so much to learn. Even say you wait, you think, well, we're going to take a lot more fluids courses. Even by the end, you might not have even touched in any more detail that specific field. So because fluids is such a broad field, um, I don't think it's ever too early to start diving into something, and it might help you in your later fluids courses. Um, Acoustics, yeah, yeah, yeah. So I'm not sure who does. Does GP do any acoustic stuff? Okay, we do some acoustics too in our lab. So yeah, just send me an email after AJ. But like the acoustic stuff, I don't think there's any undergrad fluids courses that will do acoustics. Even grad, I don't think we have any grad courses in acoustics. It's a very specialized field, but I mean, it's really important, especially like these EV tools. Like, imagine everyone has their own personal drones. Like, I don't, drones are annoying, right? The sound is like really annoying. So acoustics are going to be um, very important for those designs. Yeah, yeah. Just send me an email. Maybe we can chat after. I can. Any other questions? So the future fluids courses. So fluids two, you're going to talk more about Navier-Stokes. You're going to spend some time on more on boundary layers. So I kind of gave some correlations, but you're going to have lots of fun in fluids too with boundary layers and the theory of boundary layers. You talk about potential flow. So potential flow and the potential flow leads on to aerodynamics is this kind of analysis technique without viscosity. So you say at a very high Reynolds number, we're going to pretend we don't have viscosity. Um, and that makes the analysis a little bit simpler. You'll learn more about turbulence and also you'll cover the basics of compressible flows. I have some of the other kind of options and courses here. The ones that I want to highlight are probably from the experimental side. Experimental methods in fluids is a good class. So you're going to talk about these different experimental measurement techniques. It's very kind of broad, and you'll also get some hands-on experience. Usually that class involves a project where you're going to actually work in a wind tunnel and use a couple of different techniques. The CFD class is also good in terms of how to solve Navier-Stokes numerically. So you'll get some experience there. You'll cover a bit of theory of CFD, but you also gain a lot of like that's designed to teach you how to actually practically use CFD and what a typical problem is and what you should look for in CFD. These other classes, they also might be really good. I'm just very not familiar with them, so I can't really talk too much about that. And I've talked way too much about aerodynamics in this class already. So, yep, yeah. I don't know anything about the fluids courses being offered in Department of Science. Yeah. I'm not sure. Fluids is normally like in the university, fluids is normally done like applied fluids, all this stuff is done in the mechanical engineering department. That's pretty typical. Sometimes in terms of like turbulence and math, they would do that. Yeah. Yeah, turbulence, right? Yeah. They call it fluids. It's probably less applied though, I would imagine. Systems engineering? Is it different than the class that they just taken? Do you know? Yeah, yeah. So, but in terms of like science and the math department and stuff like that, do you know about any classes they have? Okay, yeah. The math department, like turbulence is studied, as I mentioned, like from a math point of view. So a lot of math departments, I wouldn't be surprised if they have some turbulence stuff, but um, turbulence gets very mathy. Any other questions? There's also this course I want to highlight that's being taught by JP. So JP is a professor here, and um, he's created this online course. So it's a 16-hour asynchronous course. It's kind of, you can think of it as like one of these credentials you can sort of get or something that would help your resume stand out. But this course is about CFD on HPC systems. So as I mentioned, most CFD companies, fluids consultants are using cloud computing, which is what HPC is. So basically, HPC means not running on your laptop or your workstation. It's going to run on Microsoft systems or Amazon systems, or if you're doing research, it will run on Compute Canada systems. So yeah, so it's 16 hours. JP said there's a synchronous version being offered this summer. Synchronous meaning you kind of follow along with the instructor. Asynchronous meaning you just take whatever time. So yeah, if you're interested in more CFD, it might be worth looking into doing on your next co-op term. Yep.
So that would be not in person, right? Like that would be
Yeah,
just
this
like
is all just on GitHub. It's like an online course. Yeah,
also just like
I'm not sure. Do you know? Okay.
we just
You haven't heard
J
about this?
P
Okay.
course.
They're in Jeep. Okay. Yep.
Including this course, what other extra information should you know before doing this, or could we just take this like immediately after this course is done, and it'd be fine, or is there just other information you need to know?
For doing HPC,
Yeah.
I mean, it's a very complicated thing. It's sort of you would get on the job training for doing CFD on HPC. This gives you the fundamentals to working with HPC systems, what's going on. And then, for example, you work at a company, um, you get to learn exactly how they're kind of hooking into the HPC system. Yeah. Yeah. No, I think this is, as far as I know, this is basically outside the university. Like this is a GitHub kind of course you go through by yourself. That's as far as I know. So don't quote me on that.
They
Yep.
have a list of prerequisites.
Okay.
So tell them. Oh,
Okay. So prerequisites are like, yeah, this is meant for undergrads who are like very into CFD and maybe want to work on CFD, or say you want to do your own CFD startup someday and come up with an algorithm and sell it. I would recommend this, but it takes like an intro knowledge in fluids, which I would say you all have. Um, this will also give you an intro to working with like Linux systems, because all CFD is basically done on HPC with Linux systems. Okay. So any more questions about this? I have to wrap it up. I want to close the course by just talking about very bird's eye what we should think about when we do fluids. So you have three options. You can avoid doing either CFD or experiment, which is almost always the best option due to cost. CFD is cheap to run, experiment is expensive to run, but they have the inverse problem. So in CFD, you can know whatever information you want because your fields are all stored on your computer. You know exactly what they all are to perfect precision. But the issue is because of the models, you don't know that you actually have a valid solution. In an experiment, you solve something in the real world. You did an experiment, but now you have to figure out how to measure it. So there are two different approaches to kind of the same problem. But in the real world, you likely want to avoid doing either and use analytical techniques wherever possible. So that's what's done, I would say, in the majority of engineering cases, but there's still a lot of CFD and experimental work done in the real world. I'm out of time, so I just want to say thank you. This course has been fantastic. You guys have been fantastic. Everyone here has been really fantastic, and you're all very intelligent. It's been very exciting to teach this class, highly rewarding, and I can't thank you enough. So thank you.